My name is Farad Zadeh. I'm one of the astronomers in the Department of Physics and Astronomy. I want to thank you all for coming to our first lecture of Phyllis and George Halborn Radio Astronomy series this academic year. This series is supported by the family, the Halborn family, for the last few years or so. In fact, this year is the fourth consecutive year that we've been organizing this series of lectures. And we have now a quarterly event, basically one lecture per quarter, focusing on radio astronomy. So we are really grateful for the support that the Halborn family has given us in the last few years or so, and for the funding support, and of course the chair of the department, who's really also supported us, encouraged us to sort of do this series, as well as providing the funding for videotaping this series. So this series is actually videotaped professionally, and you can actually look at all of the talks that we've had in the last few years on our department website. So today I want to welcome our sort of guest, sort of distinguished speaker, David Neufeld, who is a professor of astronomy in the Department of Physics and Astronomy at Johns Hopkins University. He is originally from England. He went to Cambridge for his undergraduate, and then he came to Harvard, working with Alex Delgado, and he got his PhD there. In, let me see, should I say the age?
No, you can if you like. 87.
87,
Yeah,
87.
A long time ago.
Right. And then he sort of went to Berkeley to do a postdoc job, working with McKee, and then he came to Johns Hopkins and has been there since. So it's a very simple sort of trajectory. And his main interest really related to molecular spectroscopy, astrochemistry, and basically using satellite observations in submillimeter and far infrared. And also he's interested in astrophysical measures. And more recently he's been interested in dark matter. And we've heard some of you were here yesterday. He gave a talk also on dark matter. He has received the sort of National Science Foundation Young Investigator Award, and also received Bach Prize from Harvard University in 1996. And we've really enjoyed having him so far. And
so far.
We're
I'll try not to change that in the next hour at least.
Anyways, he's going to talk about small interstellar molecules and what they tell us.
Great,
And
well,
by the way, just sorry, we have pizza at the end of the hour, so don't leave. Yeah, sorry, go ahead.
Okay. Well, thanks very much for inviting me. I've had a great visit as well. And I'm also very honored to have been asked to give a talk in this fantastic lecture series. And I can say, I know it's fantastic having rooted around a little bit on this website. So one of the striking things about our universe is that it's full of molecules, and not just on Earth and on planets, but also in the atmospheres of cool stars, and even in the very diffuse material between the stars. In other words, the interstellar medium, where the particle densities might be only a few hundred particles per cubic centimeter, and yet these are regions that are rich in molecules. And certainly in the cooler parts of the interstellar medium, there's a rich chemistry operating that forms and destroys interstellar molecules. And for me, the formation of molecules in this very simple environment is really a beautiful and dramatic demonstration of the emergence of complexity in the universe. So you just start with atoms made in stars, and you have them in this very low density gas, and molecules emerge. And in fact, to date, more than 190 interstellar molecules have been detected over the past 80 years. And this has been primarily, almost exclusively, thanks to radio astronomy. So in this introduction, I thought I'd just give a list of the molecules that are now known to be constituents of the interstellar gas. And they're ordered here by the number of atoms. So we start with simple diatomic molecules, and we have now specific identification of, for example, a 60 carbon atom molecule, which is the famous buckyball, the vertices of a soccer ball occupied by carbon atoms that have been now unequivocally identified in the interstellar gas. And this is an interesting list. I mean, there are some things that are very familiar that you could find in your kitchen: sodium chloride, water, carbon dioxide, ethanol, acetic acid, and some very exotic and reactive molecules that you would not find in your kitchen. In fact, some of these molecules were first identified as unknown spectral lines obtained at radio telescopes and only subsequently synthesized in the laboratory. So this list grows. This is a couple of years out of date, and I sort of update it periodically, and I always have to reduce the font size to fit them all on this slide. So that's sort of fascinating to look at, that table. But I think this field now, with careful interpretation of the results, can be more than just stamp collecting. Hey, look, we found a new molecule. Because carefully interpreted, and this is what I want to argue in this talk, observations of interstellar molecules can provide unique information of general interest to astrophysicists, not just astrochemists, about the environment in which these molecules exist. And this is quite a multidisciplinary field in that to interpret these observations, you really need a detailed understanding of fundamental physical and chemical processes involved. And this comes either from theoretical calculations or from laboratory measurements. And this field is known generically as laboratory astrophysics. And in fact, there's a new division within the American Astronomical Society that focuses on just this lab astro. The other thing that I'll try and bring across in this talk is that it's the small molecules that were in the title of my talk, which I think show the greatest promise for advancing our understanding, because the chemical pathways leading to their formation are relatively simple. So we could call this subfield molecular astrophysics. There are basically three ingredients that are needed. There's laboratory astrophysics and related theory that's needed for a number of things. For spectroscopy, to even allow you to identify these molecules, you need to know the frequencies of their spectral lines to 1 part in a million or so. So you have to do laboratory spectroscopy. You need cross-sections for the excitation of these molecules in inelastic collisions. You need chemical reaction rates. You need to understand, in fact, reactions catalyzed on the surfaces of what astronomers call dust grains. These are basically sub-micron sized solid particles in the interstellar gas. You need to understand photoionization and photodissociation of these molecules by ultraviolet radiation that pervades the galaxies because it comes from all the hot stars in our galaxy. And then there are the observations. We can observe emission lines emitted by molecules. Or if the molecules lie in the foreground to a bright background source, we may be able to see absorption lines. And then the third sort of element of the analysis involves detailed physical and chemical modeling of the various astronomical objects in which we may find molecules. So this would include diffuse interstellar clouds, denser clouds in the interstellar medium, and a number of other types of astronomical object. And so the idea is that by combining all three of these things, one can sort of extract information of general astrophysical interest. This is a field that has developed a lot in the last decade or so, partly due to three key facilities that have come online. And the first of these was the Herschel Space Observatory, which was a 3.5-meter telescope in a satellite observatory that had on board an instrument called HiFi, the heterodyne instrument for far infrared, for the far infrared. So that really was a fantastic development, the ability to look for these molecules from space. On the ground, there was the APEX telescope, which is at the Alma site in the Atacama Desert of Chile, which is a superb site permitting observations at higher frequencies than are possible elsewhere. And then now there's an airborne observatory that NASA operates called SOFIA, which is basically a 747 with a big hole cut in the side and a 2.5-meter telescope inside. And it gets above 99% of the water vapor in Earth's atmosphere, which allows you to observe at frequencies that would be absorbed from the ground, even from 18,000 feet in the Atacama Desert, because of water in our atmosphere. So these are all spectroscopic capabilities in what astronomers call submillimeter waves. So it basically means sort of 1 millimeter and below, say to a 1/10 of a millimeter in wavelength. What's happened over several decades is that the techniques of radio astronomy have been pushed to ever higher frequencies. So in this submillimeter wave astronomy, one's really doing the basic methods of radio astronomy, but at higher frequencies than was possible previously. And in particular, all the instruments I mentioned use heterodyne spectroscopy, just as is used at millimeter wavelengths or even centimeter wavelengths in radio astronomy, which provides extremely high spectral resolution, which you really need to identify molecules. And what's happened is it's now possible to do heterodyne spectroscopy at much higher frequencies. So it used to be sort of gigahertz frequencies. Now one can go to terahertz frequencies. And this has been made possible by new technologies for mixers and local oscillators. So you remember with the heterodyne receivers, what you have is the astrophysical signal comes in, and then you have a local oscillator at a nearby frequency, and they're combined in a nonlinear device called a mixer, and then out comes an intermediate frequency signal, which is easier to observe, which comes out of the difference between the frequency of the astrophysical radiation and your local oscillator, which is sort of a monochromatic source of submillimeter radiation. So these new facilities have led to several recent discoveries of molecules in the diffuse interstellar gas. So what I mean by the diffuse interstellar gas is cold clouds of gas, or mainly cold clouds of gas, but ones that are not dense enough to be centrally condensed because of their own gravity. So these are not as dense as the clouds where stars are forming, but they're very common in the interstellar gas. And within such clouds, thanks to these new facilities, we've observed many new molecules that I'm going to argue provide very interesting probes of what's going on in these clouds. And you'll notice they are all hydrides, by which I mean molecules containing just one heavy element, one element heavier than hydrogen, and then one or more hydrogen atoms. Now, hydrides have their rotational transitions at higher frequency than molecules that have two heavy atoms because their moment of inertia is smaller, and that means a higher energy, right? Because its angular momentum is quantized and energy is L squared over moment of inertia. So these hydrides have high frequency rotational transitions that cannot be observed from the ground typically, or only from very, very good astronomical sites, high elevation sites. And the reason is really that 3/4 of the surface of our planet is covered by a particular hydride, water. That's basically a good thing, but not for submillimeter astronomy, because the water tends to absorb also at these high frequencies. And so we have to go either to a very high mountain or to a suborbital platform like an airborne observatory or to space to observe these molecules.
How high are the frequencies?
So the frequencies are typically around terahertz I'm talking about now. So sort of a half to 2 terahertz is pretty much would include everything that I'm talking about here. So starting with Herschel, we've been doing a big project on observing molecules in absorption towards background sources. So the idea is sort of shown here. We're here at the sun, and there are various bright sources of continuum radiation that can be observed all the way at great distances within the galaxy at these frequencies. These background sources are not what we're really interested in, except that they provide a sort of background lamp because these are regions where massive stars are forming and are heating up these small solid dust particles, which then radiate at terahertz frequency. So that gives us sort of a background lamp. But what we observe is all the foreground gas along the line of sight. And this is actually a very clean experiment because at the densities of these diffuse foreground gas clouds, most of the molecules I'm talking about will be in the ground state. Basically, we don't rely heavily on a model for the excitation of the molecule in order to get a very good quantitative estimate of how much of the molecule is present along the sight line. So let me show you examples of the types of spectra that we can observe. So this is the intensity of the radiation, really as a function of frequency, but astronomers tend to interpret frequency as Doppler shift. So basically, differences in between frequency and the known rest frequency of the molecule are interpreted as a velocity shift. So that's what is shown here in kilometers per second. And on the left, you see the spectra for 4 molecules, 3 of them observed from the ground, 1 from Sophia, all containing the element sulfur. And you can see the sort of a broad emission line from the background source. But then you see these tiny little notches here, which are now expanded. And you can see that there are several distinct components along the sight line that are absorbing the radiation from hydrogen sulfide. And so we can get quantitative estimates. These we would interpret as individual clouds along the sight line. And they're separated out in frequency or velocity because the galaxy is differentially rotating. In other words, the angular speed is larger as you go in. So that means that where it is along the sight line will give you a Doppler shift that depends upon the location. So these are the kinds of data we can get. And you can see these are very, very high signal-to-noise spectra revealing a series of clouds containing these different molecules. So this is now the list of all the different hydrides that have been detected in the diffuse interstellar gas. And you can see that roughly half of them have been detected in the last 10 years. And then what I'm showing in this column is the abundance, the relative abundance, compared to either hydrogen or molecular hydrogen, atomical molecular hydrogen. And these are typically quite small, so parts per billion in some cases. Part of the reason they're small is that these heavy elements, carbon, oxygen, nitrogen, sulfur, chlorine, and argon, are all orders of magnitude less abundant in the galaxy than hydrogen. And that's just how things work out with the synthesis of elements in stars. So these are sort of trace elements. But even so, the molecules containing these elements typically account for only a small fraction of the element in question. And that fraction is given here because we know what fraction of the gas is in various different elements. Now with these molecular observations, we can say what fraction of all the carbon is in, say, CH or CH2 or CH+. So what did we learn from this? Well, I'm going to go through how, with a careful interpretation in the context of an astrochemical model, we can get unique information of general astrophysical interest. And I'll describe 3 examples of how we can do this with different hydride molecules, small hydrides. And in fact, different molecules that we can observe are highly specific as probes of different aspects of the interstellar medium. And this all really comes down to thermochemistry, which is explained in this next very busy, complicated, color-coded slide that I'll go through sort of a little bit at a time. So I've listed here elements that one might hope to observe, or well, all of which have been observed in the interstellar gas. And the first column here shows the ionization potential in electron volts. And this is very, very important because hydrogen is the dominant atom, and its ionization potential is 13.6 eV. So any radiation that is more energetic than 13.6 eV, h nu greater than the ionization potential of hydrogen, will be absorbed by hydrogen atoms, photoelectric absorption, and therefore will be absent within these clouds. And as a result, all these elements that have ionization potentials larger than that of hydrogen will be mainly neutral in the diffuse interstellar medium. On the other hand, if you have an element like silicon or phosphorus or sulfur or carbon with an ionization potential less than 13.6 eV, there'll still be quite a lot of starlight between its ionization potential and that of hydrogen that gets inside these clouds and will be enough to make it singly ionized. So carbon will be singly ionized, nitrogen will be neutral, oxygen neutral, and so on. Yeah.
So there's different phases in the ISM, at least in the simplest picture. Are you
Right.
talking about the cold neutral medium?
Yeah, so I'm talking here entirely about the cold neutral medium, which occupies only a small part of the volume but contains more than half of the mass of the interstellar medium. There's these other phases of the interstellar medium that are at 10,000 degrees and even some at 300,000 degrees that are not part of this conversation because they don't have any molecules in them. Yeah. Any other questions?
What are the units for the numbers?
So the units here, well, this is electron volts. What I'm showing in these numbers is the endothermicity of the reaction in question, and I have 3 types of reaction, in units of Kelvin. So really the energy, the endothermicity divided by the Boltzmann constant. Where a cell is shown in green, that means that the reaction is exothermic, meaning, of course, that the reactants have more energy than the products, and so the reaction in principle could be rapid at low temperature. Where it's shaded red, or solid red, that indicates that the reaction is endothermic, and so you would only have that reaction be rapid if the temperature is quite a lot higher than the typical 80-degree temperature of an interstellar gas cloud. So the first box is this one here that I want to talk about, and this is for the element fluorine. And the fact that it's green means that fluorine atoms can react exothermically with H2 to make hydrogen fluoride. In fact, fluorine is the only atom in the periodic table that can react exothermically with H2. And in fact, that reaction is one of the most extensively studied bimolecular chemical reactions there is. It's been extensively studied both in the lab and theoretically. Room temperature experiments show that there's sort of a barrier to the reaction that's equivalent to about 500 degrees, so that the rate of the reaction would be falling off quite rapidly, say, below 100 degrees. But for one thing, and that is the phenomenon of quantum mechanical tunneling, which means that even if you have a collision between two particles that lack the kinetic energy to get over this barrier, there's a certain probability of tunneling. So this suggested then that at low temperature the rate might be quite a lot higher than what you would get or what you would expect from laboratory measurements if you simply fit the laboratory measurements within a so-called Arrhenius expression. And this now was confirmed and actually determined quantitatively by a laboratory experiment down to about 20 Kelvin, which was quite a feat. Basically, then this experiment supports the theory that this reaction would be quite rapid at the typical temperature of these diffuse clouds, which is about 80 Kelvin. So what this means is that as soon as you have a cloud containing any significant amount of molecular hydrogen, there'll be a rapid reaction to give you hydrogen fluoride, which would be a major reservoir of elemental fluorine in clouds that contain H2. So what I'm showing here is how we would expect the abundances, the relative concentrations of these various species to vary as we go into a cloud. So if you imagine there's some interstellar cloud, its edge is here at 0, and it's being irradiated from the left by ultraviolet radiation. So we'll start out with carbon singly ionized. We measure depth here in terms of the number of, it's very close to the number of E foldings in the radiation field. So we go from carbon plus to carbon monoxide as we get successively more shielding by little dust particles in the cloud that absorb the UV. But what we find is that hydrogen fluoride forms very close to the edge of the cloud, just like as does H2. So astronomers have been interested in molecular gas that would have a lot of H2 in, but no carbon monoxide or very little carbon monoxide. And it turns out that hydrogen fluoride would be very good for tracing such gas. And this is something that we could observe with Herschel. The fundamental rotational transition is at about 1.2 terahertz. And we observed it in absorption in almost 50 diffuse clouds in the disk of our galaxy. And here are the spectra. Here's hydrogen fluoride. Here at a relatively nearby frequency is water. And you'll see that the absorption by the hydrogen fluoride is even slightly stronger than the absorption by water. And this is a very striking result because fluorine is 10,000 times less abundant as an element in the interstellar gas or in the universe as a whole than oxygen. So that's nothing to do with atomic physics, that's to do with nuclear physics. Just the various nuclear reactions in stars are better by 4 orders of magnitude at making oxygen than they are at making fluorine. So this is quite a dramatic sort of vindication of our understanding in terms of thermochemistry. And you can see it in this column where I'm basically showing that in the case of these oxygen-containing hydrides, only a few in 100,000 of the oxygen atoms would be bound up as those hydrides, whereas in the case of fluorine, fully 40% of the fluorine is in the form of hydrogen fluoride. And this can be very useful for astronomers because molecular hydrogen itself is very hard to observe. It essentially has no radio spectrum, it has no permanent dipole moment, so it can only be observed really at ultraviolet wavelengths. And you can't look very far in our galaxy at ultraviolet wavelengths. But at submillimeter wavelengths, you can look all the way through the galaxy because the dust particles don't absorb very much at those wavelengths. And so the idea is then that we can use hydrogen fluoride to probe molecular hydrogen, which is the main constituent of these clouds. Yeah?
Go back one slide.
Yeah.
Is this the spectrum of just one transition? I mean, which
Yes.
window should I be looking at? Or
So this is the spectrum of a single transition. And basically you can see that there's gases present at a large range of velocities along our sight line. This source is quite distant in the galaxy. So basically there will be clouds close to the sun around 0 and close to the source around here and everywhere in between. And you can see this is very high signal to noise. So this is real. This is real gas at that particular velocity, which if we understand the rotation curve of the galaxy, we could map to a particular location. So you can see this is a very powerful probe all the way between us and this background source. We can see exactly how much hydrogen fluoride and then by inference how much hydrogen, molecular hydrogen is present.
And the next transition is so far away.
Yeah, so this, the next transition will be at twice the frequency. It will be J equal 2 to 1. So that would be 2.4 terahertz. Some of the molecules have hyperfine splittings that make things much more complicated. And there we may have multiple transitions close together. And then we have to try and deconvolve to get the actual distribution of the absorbing gas in velocity space. But this is a very clean case because it's a singlet sigma ground state. So there's no significant splitting. Because it can be destroyed by photodissociation. And also, say it again?
It looked like as you went to higher AV, it stayed constant.
Yes. So let me just... Right, so, but we're probably looking in this region here, actually. So here you can see where these two curves cross. This is fluorine, this is hydrogen fluoride. So at this point, it's 50% hydrogen fluoride. And then here it's maybe 80%. So basically averaged over what we're looking at, it's about 40%. Actually, the lab data was very important here because the rate actually measured in the lab was somewhat lower than the theoretical prediction. So this was actually made before the laboratory measurement. So this curve might come down a bit with with this new laboratory measurement. It's very hard to model theoretically because, as you can imagine, with quantum mechanical tunneling, there's going to be sort of an exponential dependence on the height of the barrier and the width of the barrier. So it's hard to get right theoretically, and it was about a factor 2 lower as measured in the lab.
The rate would be faster for atomic hydrogen. Is the population too low?
So atomic hydrogen with fluorine. Yeah, so we're at a very low density here, so it's only bimolecular reactions that count. So
Still bimolecular, though.
yeah, so H plus F goes to HF, but then you would have to have a photon emitted, so it'd be a radiative association. So those reactions are very, very slow. Whereas this, with H2, there's a hydrogen comes off to carry off the excess energy.
These are also, excuse me, just in diffuse. They're not landing on dust grains first, and then.
Right. So the H2 is made on dust grains, but it's all reactions in the gas phase once the H2 has formed, at least according to all the models. Okay. How am I doing for time? I think I will skip over this second application, except to say that, as I've sort of implied, not everything reacts exothermically with H2, and particularly if you have carbon, either neutral carbon or singly ionized carbon, or sulfur and singly ionized sulfur. None of those species can react exothermically with H2, and yet we see a lot of CH and CH plus and SH plus, far more than we would expect if these reactions were as slow as you would expect them at 80 Kelvin, which would be, to say, almost infinitely slow, because e to the minus 4,000 divided by 80 is essentially 0. So what that provides us with a probe then of the possibility that some small fraction of the volume is filled by hotter gas. And so that's the conclusion from the fact that we see a lot of CH plus and SH, that some small fraction of the interstellar clouds are at a temperature much larger than 80 Kelvin. And this may be related to the dissipation of turbulence in the interstellar gas, either in shocks or by other mechanisms. But I'll skip over that and spend the rest of the talk on one final application, which is obtaining estimates of the cosmic ray ionization rate, or the cosmic ray density in the galaxy. So basically, a little over 100 years ago, the cosmic rays were first discovered by Victor Hess. This is from a photograph from 1911 that was reprinted in the New York Times in 2012 to celebrate the centenary of the discovery of cosmic rays. And here you see Victor Hess in a wicker basket. And you can't see this here, but he has with him an electroscope, and he's going to go up to 17,000 feet. And the electroscope is basically a way of measuring the ionization of the air. So how long does the leaf stay up? And the expectation was that as you went up, you would actually find that the ionization of the air was less, because it was believed that the source of ionization was probably radioactivity in the Earth's crust. But actually, when he went up to 17,000 feet, what he found was that the ionization rate was, or the ionization of the air was larger, suggesting then that the source of the ionization was cosmic in origin, was not the Earth. So this is always fun to show those of you who are familiar or do balloon-borne experiments. So you'll, this is really a wicker basket, not some very high-tech gondola, and the PI is inside the basket. So he got the Nobel Prize for this work in 1936. And of course, now we know a great deal about the cosmic rays. In fact, it's quite remarkable the range of energies over which they're observed. So basically, this is the energy in electron volts, and the scale here goes from 10 to the 9 to 10 to the 21 electron volts. And there's sort of well, everything looks like a power law on a log-log plot, but basically there's this, reasonably approximated by a power law over some regions for the flux of cosmic rays as a function of the energy. So the most energetic cosmic ray detected to date has an energy of 50 joules. So these are, as you know, ultra-relativistic nuclei, protons, and electrons. So this is a single proton with a kinetic energy of 50 joules, which is the kinetic energy of a fastball thrown in Little League Baseball. So it's not Major League Baseball, but still. So this is really quite impressive. It's a very interesting area of astrophysics. And one interesting thing also is that the energy density of these cosmic rays is actually somewhat larger than the energy density of starlight, of the cosmic microwave background, or the galactic magnetic field. There's a table from Bruce Drain's book on the interstellar medium that lists the energy densities for a number of things, and they're all of order 1 electron volt per cubic centimeter, but actually it's the cosmic rays is the largest of any of these. So when you look up at the night sky, you sort of think, oh, it's light, that's what the universe, the galaxy contains, but actually it's really cosmic rays. And these cosmic rays interact with the interstellar gas. So if they're what I'll call high-energy cosmic rays, they can produce neutral pions that then decay through gamma rays that can be observed with gamma ray satellites like Fermi. But for this talk, or for this context, the interesting thing is that the lower energy cosmic rays ionize and heat the interstellar gas. So a cosmic ray can interact with a hydrogen atom to produce a proton and an electron, or with a hydrogen molecule to produce the H2 plus molecular ion. And you might say then, well, we observe cosmic rays. What ionization rate do you think we should get from experiments like the one Hess did in his wicker basket, obviously much more sophisticated now? And the key obstacle really is that the ionization rate is really dominated by the lowest energy cosmic rays, and in fact lower energy cosmic rays than any that can be detected. And one of the issues is that at the location of the Earth, the sun's magnetic field and the solar wind basically reduce the flux of cosmic rays below about 1 GeV. So you can see this quite dramatically. So this is this energy spectrum of cosmic rays observed by balloons. So that's at 1 astronomical unit from the sun. But now there's the Voyager spacecraft. There were 2 of them, you remember, and the first one is now beyond about 120 astronomical units, that is Earth's orbital radii, from the sun. And this is what we're seeing now, because these so-called solar modulation effects are now either much less than they were or perhaps completely reduced. This remains a controversial question as to whether Voyager 1's really passed completely into the interstellar region unaffected by the sun. But if
the satellite measuring this?
how's the spacecraft? I mean, direct detection, but
So they have a little detector?
yeah, they have a little detector on it. I don't know much about the details. And it's sensitive to cosmic rays down to about 3 MeV. So basically, if you would extrapolate this in some reasonable way, you would conclude that then in the interstellar gas, you would expect hydrogen atoms would be ionized by cosmic rays at a rate of about 10 to the minus 17 per second. But there are 3 critical caveats about this. One, I've already mentioned, is Voyager really in the interstellar medium yet? Second, even if it is, we still have to extrapolate this curve. And then thirdly, of course, this only applies to the general vicinity of the sun, and it would be interesting to know if the cosmic ray density is different elsewhere in the galaxy. That might give you a clue to the origin of the cosmic rays. So then we can say, and what I want to argue is that by observing molecules, and particularly molecular ions, so positively charged molecular ions, we can infer the cosmic ray ionization rate, the rate at which a single atom of hydrogen would be ionized. And if you do this in dense molecular clouds, the types of clouds where stars are forming that have densities perhaps 10 to the 4 per cubic centimeter, and you observe, say, this molecular ion, HCO+, this is with a 13 isotope of carbon instead of the 12 isotope, you get a number that is in excellent agreement with what you would have expected from Voyager. But there was a very interesting thing happens that in diffuse molecular clouds, so these are clouds that are not dense enough to form stars, but still dense enough to have some molecule or significant amount of molecules. We can probe the cosmic ray ionization rate with this H3 plus molecular ion. So the idea is that a cosmic ray will ionize a hydrogen molecule, you'll get H2 plus, and then there's a further reaction with H2 to make H3 plus. So this is sort of an interesting object. It's an equilateral triangle of 3 protons and 2 delocalized electrons. It was actually discovered by J.J. Thomson as a species with a charge to mass or mass to charge ratio of 3. And its spectroscopy was elucidated by Oka in University of Chicago in the 80s. And it was possible then to detect it in the infrared towards stars in our galaxy. So to understand or to use this quantitatively, well, the rate at which it's formed is going to depend on the cosmic ray ionization rate, but you also need to know the rate at which it's destroyed, because you're basically going to assume equilibrium, and then you'll say formation equals destruction. And the main process that destroys it is dissociative recombination, where it captures an electron and falls apart. And that was measured in the lab in an experiment that was done by Ben McCall in the 90s. And so you have this beautifully entitled paper, Letter in Nature, an enhanced cosmic ray flux towards, this is a particular star, inferred from a laboratory study of this recombination rate. And this paper has sort of the laboratory study of the rate at which this recombination would occur, and laboratory spectra of H3+, and astrophysical spectra of H3+. And from this, they inferred that the cosmic ray ionization rate in diffuse molecular clouds, so these have only a density of a few hundred per cubic centimeter, was about an order of magnitude larger than what it is in dense clouds. So this then would seem to imply that, first of all, that at many places in the galaxy, the cosmic ray ionization rate is larger by an order of magnitude than what you would infer from Voyager, and that when you get to a dense cloud, the cosmic rays don't make it all the way into the interior. Yes, so they measure H2 directly through UV absorption of the so-called Lyman and Werner bands. So with my collaborator Mark Wolfire, we sort of revisited this with a more sophisticated model. Actually, our more sophisticated model just gave an ionization rate that was 50% higher. But what it did show is that there does seem to be a trend where clouds that are thicker, this is sort of the surface density of the cloud, clouds that are thicker have a slightly lower cosmic ray ionization rate. So this is sort of consistent with the idea that the cosmic rays cannot penetrate through too much material, that they get stopped and this would be a complicated thing to model involving magnetic fields that would interact with the cosmic rays. So then the question arose, could we press even to less diffuse clouds, so clouds that are almost entirely atomic? Can we try and estimate the cosmic ray ionization rate in them? And we were able to do that because if you look here, what we see is that oxygen, singly ionized oxygen, can react with H2 to make OH+, and singly ionized argon can react with H2 to make ARH+. But argon and oxygen have ionization potentials less than that of H2. So they'll be entirely neutral in the interstellar medium unless they get ionized by a cosmic ray. But they're certainly not going to be ionized by starlight as the other elements are. So basically, the amount of OH+, which is the product of this reaction, and ARH+, which is a product of this reaction, can be used to get an independent estimate of the cosmic ray ionization rate. So you may be surprised to hear me talk about a molecule containing argon. This is the first known interstellar molecule containing a noble gas atom. Sounds very exotic. I mean, it's sort of isoelectronic with hydrogen chloride. So if you took hydrogen chloride and added a proton to the chlorine, you would get this.
How about neon hydride?
Yes, so that's been looked for, has not been found. And we think we understand that. I won't have time to go into that. But basically, there are certain accidents of thermochemistry and of reaction rates that make argonium, ARH+, more abundant than any of the other noble gas molecular ions. But basically, this can be observed. It was widely observed, actually, but was not identified until several years later. And it, along with OH+, provides another nice probe of the cosmic ray ionization rate. So I'll just skip to the bottom line, which is that the value that we get is actually in very good agreement with this value obtained from H3+. So this sort of confirms the sort of surprising result obtained back in the 90s that the cosmic ray ionization rate is a lot larger than people had previously thought. The final way, and this I'll close with this sort of goes now to much lower frequencies and back to more traditional radio astronomy, comes from observations of radio recombination lines. So here's a spectrum at very low frequency of recombination lines of hydrogen and carbon observed actually in absorption. This is a sort of inverted scale towards a very bright source of megahertz radio emission. And we can see these lines that have very high principal quantum numbers. So actually, they've detected lines now at very low frequencies where it would be the transition between a state of principal quantum number 900 to 899. It's kind of amazing to think about these atoms, which are called Rydberg atoms, because the sort of radius of the electron cloud goes as n squared. So this would be a million Bohr radii. So these are sort of the largest atoms in the galaxy, and we see recombination lines of hydrogen that occur when H+ recombines with an electron, and the electron's captured into a state, a very high principal quantum number, then does a radiative decay. And we also see carbon recombination lines where we had carbon plus, and it captured an electron into a very high quantum state. And basically, there's just a small shift. So if you're at an electron 1/10 of a millimeter away from a nucleus, you can't really tell the difference between a proton and 6 protons and 5 electrons, carbon plus. The potential is essentially exactly the same. But there's a small shift because if you remember the formula for the Rydberg, it involves a reduced mass of the electron, and the reduced mass of the electron is slightly different when you have carbon as opposed to hydrogen. So there's a nice shift here. And what you'll see is that the ratio of the carbon lines to the hydrogen lines, in fact, the carbon lines are stronger, even though the elemental abundance of carbon is 4 orders of magnitude less than that of hydrogen. And the reason is that carbon is ionized by ultraviolet radiation, but hydrogen isn't. So these hydrogen recombination lines are basically just coming because cosmic rays ionize a hydrogen to give H+, which then recombines to make these radio lines that we can see. So the ratio of the hydrogen to the carbon lines gives us a handle on the cosmic ray ionization rate. And the value is intermediate, but quite close to what we had for diffuse atomic and diffuse molecular clouds. So I haven't had time to explain this very fully, but there's sort of a continuum as we go to denser, thicker clouds from left to right, and there's sort of a well-behaved dependence in the cosmic ray ionization rate. So I'll just leave up this summary of the various things that I've covered. HF is a tracer of H2, SH and SH plus, and also CH plus as tracers of of anomalously warm gas within the interstellar clouds, and the cosmic ray ionization rate being measured by some of those other molecular ions. And finally, I guess let me leave up the list of my collaborators on this work, both on the observational side. We had a number of key programs with the Herschel Space Observatory led by Marie-Yvonne Gérin and Ted Bergin. I benefited enormously from collaborations with the SOFIA team, and then a postdoc who's now at Space Telescope, Nicky Andriolo, did some of the ground-based observations, and then a number of collaborators, particularly Mark Waldfire at University of Maryland, on the theoretical modeling of these diffuse clouds. And this has been supported by NASA. Thank you.
Thank you so much. So we have time for questions. Okay, we'll go with you.
I wanted to review the cosmic ray density. Very, very important work, and I wanted to understand, make sure I got it right. So it decreases as you go into molecular clouds. Is that
Right.
monatomic, or is it increasing density?
Yes, so I mean, to the very limited extent that we can see it, we would say it's monotonic. I mean, this is the plot. So this is H2 column density, integral of the H2 density along through the cloud, and this is the ionization rate, and yeah, so that's sort of monotonic to within the errors.
That's what I thought. And so the question I had was, how again does that compare with what Voyager sees? Which, and then also, can you get any estimates from looking directly at synchrotron emission from cosmic rays, or are those somehow not comparable?
Yeah, so the synchrotron, probably Farhad could answer that question. I'll defer that. Maybe he'll be able to answer
Yes, you can. That
Okay.
synchrotron has another, you can also detect or measure the cosmic ionization rate from synchrotron emission as long as electrons are interacting with the molecular
And how
gas.
does that compare with these numbers?
Oh, well, the ones that I've been doing is at the galactic center. They're 2 orders of magnitude more than here. So
which
that's
is
a
also
different-
confirmed with the molecules, actually.
dense
so these,
gas, yeah.
Yeah, so these numbers I've been giving up for the disk in the center of the galaxy, both what Farhad just described and these molecules indicate much higher cosmic ray ionization rates. As to what Voyager saw, Voyager basically would infer number somewhere around here, 10 to the minus 17, But I mean, we're not in the middle of a dense molecular cloud. So then the question is, why is it only 10 to the minus 17 as measured by Voyager? So there were the three caveats I mentioned. Maybe the sun is very atypical, although we see quite a little dispersion from one cloud to another. So it'd be kind of surprising to say the sun just happens to be down here. Maybe the solar modulation effect that I talked about is still important even at the distance of Voyager now. Or maybe there's some lower energy tail that is simply below the threshold that Voyager can detect, but which still ionizes.
Thanks.
Yeah.
Very good. Yoram, you had a question? Oh, okay. Go ahead. You can.
Do these interstellar molecules and diffuse clouds ever come close to, say, emerging solar systems?
Ever come close to
solar systems information?
Yes. So I mean, basically, well, in the sense that you have a diffuse cloud, and then in the interior you might have a denser cloud, and it's in those dense clouds that the material of the gas collapses to form solar systems. Right. I don't know if does that answer your question? Yes. Yeah. But these clouds themselves would not be dense enough to form stars, and we don't see stars associated with them, these diffuse clouds. Yeah.
Yeah, go ahead.
So when you look at HF,
Yeah.
it traces both H and F, but because it seems like almost all F is captured onto H, it seems to me that and F is much less concentrated than H. It
Correct.
seems like basically concentration of HF is limited by the concentration of F.
Exactly.
So why is then this is a good tracer of H as opposed to F?
So there's an assumption here that the elemental abundances are more or less fixed everywhere in the galaxy. So that fluorine, it has an abundance of 10 to the minus 8 or so relative to hydrogen, and that's more or less the same everywhere. The interstellar gas has been quite well mixed. So if you're very close to supernova, you could have different elemental abundances. And there is a gradient, so as you go into the center of the galaxy, probably the abundances of many of these heavy elements increase just because there's been more stellar activity. But it's basically assumed, the elemental abundance is more or less fixed. But that is an additional uncertainty.
I have a question. You mentioned about the electron density of cosmic rays, cosmic energy density.
Right.
And it was a little bit higher than electron volt per centimeter cube.
Right.
And now with these new measurements, you obviously should see a higher cosmic, with the higher cosmic ionization rate, you should be able to see also a higher cosmic ray energy densities. So don't you have some kind of an equilibrium, the equilibrium between the magnetic field and the radiation field and the cosmic rays are going to be basically out of they're not going to be the same anymore.
Yes.
Because all along we were always taught that these different sort of material, they're all in equilibrium with each other.
Right.
But all of a sudden you have now higher cosmic ionization rate, higher electron density of cosmic rays, and what does it do really to the evolution of the interstellar gas?
Right. So basically, I think the answer is that that one EV probably included the higher cosmic ray ionization rate.
Oh, it does.
But also, it's actually more energetic cosmic rays that would than the ones that dominate the ionization would dominate the energy density. So changing that number may not have such a big change on the estimate of the cosmic ray
of the energy density of cosmic rays.
Yeah, but it is interesting how all these things are roughly the same. Why is that? Some of them you would expect to be the same. Maybe the turbulent kinetic energy you would expect to be comparable to the magnetic energy. But why is the cosmic microwave background roughly the same energy as starlight? I mean, in some sense, it's probably a coincidence, because if you go to a redshift of 3, the density of the cosmic microwave background is 64 times larger. But the density of starlight was probably the same. So it's kind of a puzzling near equality of all these different things. Maybe there's some anthropic principle explanation. I don't know what it is.
So we have time for more questions. I'm afraid to say that the pizza delivery is a little bit late. So it's unusual, but it's supposed to be coming any time. So just hang in there. And but we could, if you have any other questions, we could ask anything particular that you wanted to talk about, but you didn't get a chance to?
Well, I was sort of
minutes?
rushing at the end because I thought I was running out of time. I could talk just a little bit about future directions, which I didn't get time to.
That would be good.
So Herschel, which was our sort of workhorse instrument, was cryogenically cooled with just a big dewar of liquid helium. It wasn't a closed system, so it just boils away, and then when it's all boiled away, which happened after 4 years, it was the end of the mission because the detectors were no longer cool. But one thing that's very exciting now is with ALMA, which is this array of telescopes which has fantastic sensitivity compared to APEX, which was a single dish. You can actually observe some of these transitions that are unobservable from the ground in the local universe at high redshift, because at high redshift they're actually shifted to wavelengths that are lower, where the atmosphere is transparent. So there's a beautiful case where there's a galaxy at a redshift of roughly 0.9, just happens to lie in front of a radio source behind it at much higher redshift. And they've detected something like 20 different molecules in this galaxy at a redshift of 0.9. So you're looking now a reasonable way back into the history of the universe, and you can measure HCl plus, you can get isotopic ratios that might give you a clue about star formation history, and so on. So that's sort of one thing is ALMA. And then the other thing is SOFIA, which has this instrument I mentioned called GREAT, which fills in parts of the spectral coverage that there was sort of a gap in what Herschel could cover. And that's actually what allowed us to detect SH for the first time with SOFIA. And then it could also observe OH and HD at higher frequencies. And now, in the latest round of proposals, it's possible to now observe at lower frequencies with GREAT. So I just put in a proposal. I'm hoping now to be able to look at many more sight lines with SOFIA and do additional measurements of the cosmic ray ionization rate at lots of different locations in the galaxy to get a better sense of how it might vary within the galaxy.
So what kind of cosmic ionization rate are you getting in these extragalactic objects?
So I'm not sure they've... Oh, yes, they I don't remember that, actually. I wasn't involved with that work. But yeah, I didn't mention it here, but they did recently have OH+, and I'm not quite sure what they got for that.
It will be interesting to
Yeah,
compare.
it will be very interesting. Yep.
Okay, on that note, let's thank David
Okay.
again.